So thanks everyone for joining. And my name is Amrit. And today I'm quite excited to be talking about our work at the Vector Institute. So I work in the AI engineering team at the Vector Institute, and I'm a technical team lead there. And me and my team, we've been working on an open source framework. Uh, it's a framework that we wish to build as to enable guardrails for deploying ML models for health, and that's what we'll be talking about today. So a little bit about me. I'm originally from India. I grew up there and I had most of my childhood there. Towards the end of my high school, I spent some time in Fiji Islands because my parents relocated there. So that was like a very different experience for me. I then came back to India to do my undergrad and then went on to do my master's in Sweden. And then I worked in Sweden for a while before thinking of Canada. And then 4 years ago, exactly, I moved to Canada. And I got started my career in the field of autonomous driving. So my background was mostly into developing computer vision software to detect vehicles, pedestrians, lanes, and sort of the perception stack for autonomous vehicles. And I spent nearly around 3 to 4 years trying to help two different companies build autonomous driving stacks. And so that's where I kind of learned a lot about deep learning, machine learning, putting machine learnings to production grade use cases, and sort of building a software stack which can be sort of optimized for running large neural network models. Around the middle of 2021, I was starting to feel like the application area was a little too crowded, and sort of it became a little boring for me to keep trying to attack the same problem. And I was thinking of machine learning more as a general sort of thing which can be applied to different domains. And one of the domains that really excited me was healthcare. So I moved to the Vector Institute around late 2021, and I noticed that there was a lot of opportunity for applying machine learning in the healthcare domain. And so I sort of transitioned my career from autonomous vehicles and doing a lot of computer vision to actually developing applications and applying machine learning towards healthcare. So if I look at where I work today, it's basically at the intersection of three things. It's machine learning, it's open source software development, and healthcare. And that's where I found that I could contribute the most. And the framework that me and my team are working on is exactly lies at this intersection. It's all Cyclops, and it'll be what I'll be talking about mostly today. So to take a step back, when I sort of started working in healthcare to understand some of the challenges, this was around mid of 2021 and 2021. And this was when the healthcare system in Canada was really being stressed under COVID. And every day there was news coming out with, for example, a well-known hospital in Toronto put out an urgent plea for physicians, medical residents, and other volunteers to help fill in some of the gaps. There were hospitals in rural communities which were extremely short-staffed, and they were closing emergency departments and ICUs. A patient even in Victoria placed an ad in the newspaper pleading for a doctor to renew her prescriptions for her 82-year-old husband. And then a family physician published his own perspective in the Ottawa Citizen, and he had to say this very sort of sobering message where he just told that he's not able to take more patients, and he's struggling with his present load. He's overwhelmed. He's unable to answer the expectations, and that's really like sad to see, and it's very disappointing for a physician that they're not able to help patients. And so really this healthcare crisis, which sort of reached a peak last year, I think sort of is happening all across the world, but even more so in health systems like that of Canada. And so it really sort of asks a question like, what can we do to solve it from the perspective of applying machine learning and other sort of software solutions. And so digging a bit more deeper, one of our Vector staff, specifically our director of health and data strategy, Roxana, wrote an interesting article in the Toronto Star as to how AI can improve Ontario's healthcare system and lower the costs for providing effective care. And this is, something that is not new. I think for almost around 10 years, people have been talking about using data that is collected by our health system to really improve efficiencies, improve patient care. And so in the last several years, especially, after the revolution of machine learning and deep learning took off, there's been a lot of research that has demonstrated that ML and AI technologies could be used in the healthcare setting. However, this also sort of opened up a whole Pandora's box of different initiatives and different people coming together to start trying out or trying to apply AI in healthcare. And so currently it sort of feels like a wild west when it comes to AI adoption in healthcare, where health systems which are struggling, they are really looking for out-of-the-box solutions, and they feel like AI can help solve some of these problems. But the problem is that like AI itself is a very nascent technology, and it's very prone to errors, and it's prone to failure. And putting AI to deployment in such a high risk and high safe environment is very challenging, where patient safety and dealing with important decisions is very, very tricky. And so navigating this whole landscape is very challenging at the moment, and regulators and healthcare practitioners are finding it very difficult to answer questions as to how AI models should be regulated and who should be overseeing them, what are the things that we should be looking out for, and all of these things. And so what a research team out of a few hospitals systems in the US started looking at this problem more closely, specifically a team at Johns Hopkins started looking at this problem where there's a lot of these AI models being tried out or deployed at hospitals, but they're done in a very sort of ad hoc manner with no proper guidance from regulators. And so the messy truth about AI in medicine is that there are very ad hoc decisions being made. There's no transparency, and there's a very sort of individualized approach. Like one approach that works in a hospital just cannot be applied to another hospital. And this is very challenging because as a whole field, you cannot do research where you can compare results and talk about shared results if you cannot sort of generalize across different domains and different environments. And one good example of this is that a common problem that occurs in hospitals is that of sepsis. So patients who are admitted in the hospital and they've been receiving treatment can have septic shock through bacterial infections and other problems such as organ failures. and this is one of the leading causes of death in hospitals. And so a while ago, there was a popular company, an EMR company, that implemented a sepsis prediction model in the EMR itself, so that doctors could be alerted when a patient is going to be is susceptible to septic shock. And this particular model was trained on their proprietary data set, which consisted of data from several US hospitals. And then eventually the model was rolled out to a different set of hospitals. And when a research group came in and evaluated this model, they found that it really falls short on patients from the hospital in which it was deployed on. So the accuracy levels and the scores, the performance scores, really dropped in the hospitals where they were looking at. And so this really raised an alarm where these proprietary models and these closed source models actually are being deployed without proper regulatory oversight. So in a sense, after this particular paper came out, a lot of proprietary models were deemed to be problematic, and physicians and other clinical stakeholders started losing trust in these models. And this really raised a problem for AI research within medicine, because if clinical staff don't trust AI models, then no matter how much research you do, you cannot go in and deploy these models. So there is really a big need for improved transparency across all stakeholders, and this is really the problem that is sort of preventing models from being deployed today, amongst other technical challenges. So Cyclops is an initiative that me and my team started working on sometime last year. It stands for Cyclical Development Towards Operationalizing ML Models for Healthcare. So obviously that's a very uncatchy title, whereas combining cyclical and operationalization, you can form the word Cyclops, so that was more catchy. In any sort of ML operation cycle, you have typically three main components: the data, the model, and the deployment of the model. And these three things are very closely interact with each other. So you start with formulating the problem whenever you've identified one. You define the inputs and outputs, and then you start formulating the representations from that raw data. You choose different models, train them, you analyze them for performance, and finally you create inference pipelines, serve the model predictions, and evaluate and monitor it over time to achieve deployment. So in order to facilitate these three things, which typically happens in this sort of cyclical feedback loop, we started building APIs. So for example, to enable researchers and engineers to fetch data from a stored database, we started working on a query API. And this data, once extracted, needs to be processed. It needs to be cleaned such that it can be you can extract useful feature representations. So we started working on a process API, which then can be standardized into a data set, and the interfaces to work on this data container can help researchers do things like analysis, plotting, and stuff. And so that led to the data API. Once you have the data ready, you can start doing some interesting modeling. And so in the modeling part, I'll be talking more about the tasks API, which is much more related to the healthcare context. And then one of the most important things about Cyclops is that it helps you evaluate models. And so we built an evaluate API, which can help evaluate models across different dimensions. And once you have figured out how good a model works, you need to be able to monitor it over time so that you can observe when the model is likely to fail and come up with strategies to either update the model or retrain it, take it offline, and so on. And finally, you want to be able to connect all of these things and sort of provide a transparent and thorough oversight into the way the model works and the overall system. So in order to do that, we are working on a report API where you can start generating reports and model cards that basically talk about the model, the performance, what data set it was trained on, and all the other details that can help inform stakeholders about the model. So to begin with, I'll talk about the query API. So if you look at how clinical data is captured and stored, you can look at like popular data sets such as Mimic, which is a freely available data under a credentialed license, or EICU, which is a large ICU collaborative data set across multiple hospitals in the US. All of these data sets, they are typically retrospective data sets. So what happens is that they've managed to capture and collect data from hospitals from different EHR systems and store them in a relational database. And so typically relational data, you can use a tool such as Postgres SQL to be able to store the data and sort of allow users to query it. And usually, so it serves as the database or the data lake where you put data and you then query to retrieve the useful parts that you're interested in. And if you look at hospitals today, they capture data in these large relational databases along with other sources such as like clinical notes, radiology reports, etc. And they implement a standard so that the data is stored in a unified format. And this is known as the HL7 standard. For real-time deployment and for exchanging this data, there's a popular standard that is being adopted called FHIR, which stands for Fast Healthcare Interoperability Resources. So where you use well-known sort of web standards like HTTP methods and so on to query data and receive them in well-known web formats. And so this is usually how clinical data looks like. And so when you go to a hospital, either you're looking at data that is stored in a relational database that you can like use tools like Postgres, or you have something like an FHIR or FHIR server, which you can use to fetch data by talking to the various endpoints of the FHIR server. So a lot of researchers, they work with the former part, which is like relational databases. And typically you use SQL to query these relational databases. It turns out that SQL is quite simple and it's easy to learn. It's quite, it serves its purpose, but then it can also be painful when it comes to using it towards ML applications. So here's an example where I've created, I have a snippet of SQL code where I'm trying to gather some columns and some fields from a few different tables. I'm trying to join them with another table, and then finally arrive at the resulting table by having some conditions. The code is fairly easy to understand, but the problem is that this is not very easy to extend or parameterize. So let's say I want to change something in here and parameterize it using a function, I'd have to actually go into the code and change it and rerun it every time. And also, SQL code tends to be very repetitive. So you could be doing the same kind of joins and select statements in a lot of different places. And so SQL code tends to be like big and clunky. And when you try to combine your SQL code with machine learning code, which is typically in Python, the code base itself can be somewhat hard to maintain. So what we thought would be a good idea to address this problem early on when we started working with the raw data, with raw clinical data, is that if you have a database, in this case, it's a relational database, can we build a simple Python API on top of like existing libraries and have a simple way to query data without ever having to write SQL code? And so we wrote an API to do this called the Query API, where you simply instantiate a high-level dataset querier object, and it has some useful methods to be able to fetch different tables, different columns and stuff. And you can apply low-level query operations, which sort of resemble all the different operations that you can do with SQL commands. And all of this is using a Pythonic sort of API. And the result is that you get a data frame, like a pandas data frame, which most ML folks and data scientists, they're comfortable with. So I want to just show this in a quick tutorial. And I want to showcase this using the popular Mimic4 dataset. So the Mimic4 dataset is a large EHR database that's available through the PhysioNet interface. So PhysioNet is a sort of repository of many health and medical data sets. So for researchers who are working in this field, it's quite a popular one where they can go and work on like public data sets. So what we do to use the Query API is we simply import it from cyclops.query. We pass in different parameters that can help it connect to the actual Postgres database, like the user, database, password, host, port, and all these information. And then let's say that as an example, you want to get all the patient admissions from the year 2021 or later. So of course, the year of care here is de-identified, so you can only get approximate year of admission. So what you can simply do is there is a table called the patients table, and so you can simply get a query object by calling that function. And you can define a list of sequential operations to apply on this table. So for example, here I applied two operations. One is called an add delta column operation. So what I'm doing is I simply add an anchor year difference to the admit time and discharge time columns. And then I apply a condition where I say that the admit time has to be after 2021. January 1st. So this will basically do a filtering condition such that the admit time column is filtered to have only those rows where the admit time is greater than the 1st January 2021. And so then I can just pass the list of these operations and join it with the admissions table, and finally call a simple run method to actually run the query. And so the admissions result here is actually a data frame with 1,575 rows. And so with this Query API, you can do a whole bunch of other operations. So you can, like, for example, do substring search. So if you have like a string column, you can search for specific words. You can apply a condition such as like condition in years. So if you have a date time column and you're looking for that column date time to appear in a certain year, you can do that sort of a filtering condition. You can also have regex match conditions. So if you're looking for, especially like, for example, when a lot of notes or text data is captured, you would need to sort of do regex matches and those sort of conditions. So you can use that to like filter the data. And you have a whole bunch of other examples, such as joining with other tables, being able to apply like exact equality conditions, and so on. Let me go back. So that's basically what the query API allows you to do. It allows you to write very simple Pythonic code to do what you can do with SQL. So next I'll be talking about the process API. So when you look at patient data or generally data that's captured in a hospital, you have a timeline of events. So let's say the patient is admitted in the evening at 6. Immediately after admission, there are usually some tests being done, like lab tests. The admitting physician writes down some notes. Maybe the patient has some medications. So all of these are usually captured in the electronic health record. And so they're all with basically data which have timestamps associated with them. And so when you look at this data, you're looking at you're looking at sparse data and data that is not aggregated into like equal bins. You're just looking at points, and each of these points corresponds to a particular timestamp and a value. Potentially, there are other attributes such as like the name of the test that was conducted, what unit of measurement it is, the actual result value. And so when you want to use this towards any sort of clinical task, such as predicting the risk of patient mortality, what you do is that you try to aggregate this information and then pass it to your ML model. Let's say, for example, you're aggregating the first 24 hours after admission, and then you make a prediction then. What you're actually doing is that you're asking the question, so this patient has been there 24 hours in the hospital. What is the risk of this patient dying? And so what you're really doing is to capture all these different raw data, including like clinical notes and things like that, and convert them into useful feature representations, and then make a prediction using those. So if we look at the broad range of data, you can segregate them into static and temporal data. So static data is anything that is static across the patient encounter. So for example, the age of the patient or the sex of the patient remains static during the time of, like through the time of the patient's journey when they're admitted. Whereas temporal data really captures the dynamic changes in the patient's condition. So for example, different lab test results, blood pressure, heart rate, all these other vital signs, all of these fall under temporal data. And so these are the inputs. And the first module in the processing API is a cleaning module, which has functions to format the data, to convert units and standardize them, to be able to handle different types and sort of standardize them into Pythonic data types. And so once after you do some initial cleaning and pre-processing of the data, you can sort of create tabular or temporal features. So tabular features, again, are simple like tabular or table-based data, whereas temporal features are really features with multiple timestamps associated with them. So you're not just looking at a single feature value per feature, you're looking at like multiple values. And so the difference between tabular and temporal features is that you can aggregate temporal features. Let's say, for example, in 1 hour, if 3 values or 3 lab test results are calculated, you can aggregate them to say, to take either the mean of that value or to take the median or other statistic from those multiple values. And so basically we have these two containers, tabular and temporal, and we have additional sort of transform modules which help apply transforms to these features. So one commonly used transform method is imputation. So we have an imputer module where you can define different imputation methods. And the other is an aggregator module where you can define different aggregation methods and sort of pass them to these feature container. What you get out from these containers is a vectorized object. So a vectorized data container essentially contains the output data in a vectorized format. So it's instead of having these sparse data, it's a proper vector in like a NumPy array, which you can then save to disk or save to a feature store, or convert to, say, a different sort of use a different library such as PyTorch or TensorFlow. So this is sort of the high-level overview of the process API. And I just want to show you a quick example of the process API in action using an example. So this example is going to use a small subset of the Mimic3 dataset to predict in-hospital mortality. This dataset is actually available on Kaggle, and it's a small subset that captures those cases or those patients with a cardiac or a heart failure condition. So what we'll be doing is first we'll simply use the Kaggle Python API to download the data. We will load that data into a pandas data frame. And then do some simple exploratory data analysis to understand like the different qualities of the data, like for example, distribution across gender, distribution across age. And then what I really wanted to show is the use of the process API. So once you have your data, you can simply pass it to your the tabular features container and mention the list of features that you're interested in and the actual target that you're interested in. And it automatically figures out the different types, applies some cleaning to the data, making sure that it's sort of feature ready and ready to be applied for some downstream machine learning task. Okay, so now we've managed to extract some raw data from a database and we've managed to process them. How do you actually start building use cases? So you want to start looking at models and specific tasks that you're interested in. So I'll be talking about the tasks API, which in turn uses a bunch of models that we have implemented as part of Cyclops. So the tasks API is basically a standardized interface for implementing different modeling and evaluation. So for example, if you create a certain task, such as mortality prediction, or let's say you're predicting the risk of heart failure, the idea is that the task class will have standard methods for preparing the model, for training different classes of models, as well as for validating and evaluating the model. And so this kind of makes it easy to maintain the life cycle of the model, as well as like wrap all the useful things that are related to the task into sort of one container. So a quick demonstration of that. So in our case, we're going to show the same example.
Sorry to interrupt here, but nothing's happening when you're clicking these links. I apologize.
Oh.
Yeah, sorry. You're not switching to the other screen.
Thanks for mentioning that. Let me see. Okay. Can you see the other tab now?
You're all good now.
Okay, great. Sorry about that. I completely forgot that it was sharing one tab and not the other ones. let me actually quickly run through the things that was missed. So basically, the example that I'm showing is that of an in-hospital mortality prediction task. And so the thing that I was talking about previously was the use of the process API, where I'm simply using this data set through the Kaggle API. So it's a small data set that is available through Kaggle. And so what I'm doing is, first, there's some exploratory data analysis, like I mentioned, like looking at the distribution across gender, across the different like outcomes, also across age, which is an important static demographic feature, also across the different the outcomes. And so the use of the process API really comes here, where the input data frame can be passed to a tabular features class, where you pass in the actual data frame with the features, as well as the list of features. And then you mention which outcome you're interested in. And so this really captures the list of features for modeling using the tabular features. So it automatically identifies the type of the feature, and you can use this for downstream machine learning modeling. And so I was talking about the evaluate API. So once you've managed to sort of pre-process the data and creating a model, in this case, we are creating a simple stochastic gradient descent classifier. What we have created is a task API. And in this case, we've implemented a mortality prediction task. And this task you can simply instantiate with the name of the model, along with the actual model that was created. Here, again, you can use any model. So far, we provide support for sklearn and PyTorch models, as well as provide like a factory method to create different models that are either sklearn models or PyTorch models. And so once you create a model, you can simply, you will get a model that is wrapped with either an sklearn wrapper or a PyTorch wrapper. And then you can simply pass that model to a task. So in this case, it's mortality prediction task, and the list of features which are mentioned here are passed. So in this case, we're using a few interesting features such as the blood calcium level, RBC, platelets, age, heart rate, urine output, etc. So we pass the list of features, and then we mention that the target column is called outcome. And then, as I mentioned, the task API really provides standardized interfaces for training the model as well as like evaluating it. And so you can really call a train method here to be able to train it. And so this really standardizes the way you train it with irrespective of what model type you're using. So you can be using like an XGBoost classifier or an SGD classifier or a PyTorch, convolutional neural net, but the interface sort of remains the same. And then we run some predictions using the model, and we get access to the predicted labels. And now I want to actually go back to the presentation. Okay, so that was briefly talking about the tasks API. And so the next one is, once you've managed to train a model, the next important thing, and this is really the point of the framework, is that you wish to evaluate the model. And so we came up with an API to be able to perform evaluation. And typically the sort of metrics that ML scientists like to look at, like AUROC, precision recall, sensitivity and specificity, these are all sort of aggregate metrics on the entire data set, or like at least a validation set. But for clinical use cases, it's important to not just look at aggregate level metrics on the entire patient population, but rather on dividing them or looking at them across different subpopulations. And the real question is then, how do you compute, or how do you then come up with these subpopulations? One example is you could look at different age groups, or you could look at the different sexes or different ethnicities. And so really how you divide your patient population into different subpopulation depends on what you're trying to analyze. But the idea of providing an easy way to compute different patient subpopulations and evaluate your model across them is the point of this API. The second aspect is that when you want to look at the model performance across different subpopulations, you can also assess them for fairness. So if a model is deemed to be fair when it's equally performant, or it results in equal sort of equality of outcomes across different patient subpopulations. And so if you define a certain reference-based groups as being like a privileged group or an assumed privileged group, you can test the model for whether it's fair when you compare a different patient subpopulation to that base or reference group. And this is a very important analysis to make sure that your model is not trained on biased data, or the way it was trained was in a manner that would exacerbate biases in the training data. And so what we do to achieve this is we implement an evaluator module that has a compute method, which can then sort of compute the different evaluation metrics given a data set and a list of metrics that need to be computed. And that in turn is the results of that evaluation is then used to generate the actual evaluation report. So I'm just going to show an example of that. I hope you can see the new tab now. So we've managed to train this example model on the mortality task, and we also ran some prediction on a test data set here. And so now we really wish to evaluate the model's performance using different metrics. So for example, accuracy, precision, recall, F1 score, all these are interesting metrics. We can also simply create these metrics and create a list of them and pass it to a metrics collection object, which can track all of these metrics using like a single sort of method. Now, the way we allow the user to create different patient subpopulation groups is that they define a list of group filtering specifications. So for example, here, the first group is going to be patients who belong to the age group of 30 to 50. And you have, for example, you can include the minimum value, which is 30, and exclude 50. The second group belongs to patients who are from the group 50 to 80. The third group is patients who belong to gender 1. In this case, it's all male population. Then you have the female population. And then you have another example where you're putting a filtering condition on a specific column called the anion gap column, where you're also sort of setting a minimum value. And so you sort of filter on the condition that the minimum value of this particular column needs to be a certain value. So these are the different patient subgroups that you're creating. And you pass this to a slice specification object. And then this defines really how you're going to slice the data set into different patient subgroups. So now you can also define a set of metrics to assess fairness. So the nice thing about our metrics package or the list of metrics that we've implemented is that you can perform arithmetic on the metrics. So for example, if you want to create a derived metric out of an existing metric, you can simply sort of create the metric first. So specificity and sensitivity are well-known metrics. You can then create derived metrics such as false positive rate, balanced error rate, using arithmetic calculations of these metrics to finally create a collection of metrics that you're interested in. And so once you've managed to create the collection of metrics as well as define the different patient subgroups, you're ready to evaluate the model. So you pass in the test data set, the collection of metrics, the name of the model, pre-processing methods, and the slice specification. You can additionally add a fairness configuration so that besides the normal evaluation, you also have fairness evaluation. And finally, you call the evaluate method, which returns you the different results and the data set with the predictions. So the real point of this this method is that you can evaluate the model across different patient subgroups using this particular API call. And you can in this case, you can also pass in, if you already have predictions from a model, you can also pass in predictions. And if you don't pass in predictions, and if you instead pass a model and a data set, it will automatically run the predictions as well to get the test set predictions. So we're looking at the outputs. So you can, in this case, we're looking at specifically the ROC metric that was computed for the age group 50 to 60. And for example, the other ROC curve for only the subgroup, which was the female population. So you can do basically, patient subpopulation analysis, the performance analysis by looking at the results. Right, switch back to my presentation tab. So that is basically the high-level overview and an example of using the Evaluate API. We now go to the Monitor API. So when you have a model in production, and let's say you are trying to deploy this model in a hospital, one of the biggest concerns is over time, does this model continue to perform as well, given that the test data set or the patient data is constantly in flux. So the thing is that, every day there are changes to the clinical practices, there are changes in patient populations who come into the hospital. And so the test distribution, it can keep shifting quite dramatically, and it can change from the training distribution in ways that are unanticipated. And when such changes in the distribution happen, the ML model is likely to fail. And so what you really need is some sort of like a system or a subsystem that can monitor the model over time to make sure and ensure that the model is performant. And so we started thinking about this problem, and we came up with an API to run different sort of statistical two-sample tests. So basically what you have is a source and a target data distribution. Your source data typically is the training data which your model was trained on, and the target data is the data that you want to deploy on, or the current data that the model is seeing. And so one of the things that we wanted to understand is that when the target data shifts compared to the source data in different ways, how can we actually capture that shift using different statistical tests or sensitivity tests. And so what we introduced was a shift applicator, which has two parts, a synthetic shift applicator as well as a clinical shift applicator. So with the synthetic shift applicator, you can apply synthetic shifts such as Gaussian noise, binary noise. You can swap features and sort of apply synthetic shifts to see how well your shift detection approach detects that synthetic shift. But the problem is that such synthetic shifts don't necessarily help you understand whether your actual algorithm will work for the real world. And so what is more interesting is clinically relevant shifts, where you're looking at shift between different hospital types. So for example, academic versus community hospitals. You're looking at shifts across months. So for example, sometimes patients who come in during winter are, they have different characteristics from patients who come in during summer, because there are different seasonal trends, diseases, etc. You can also look at shift across specific timelines. So for example, a great example is like between pre-COVID and COVID time. So when COVID struck, the patient population that was coming into hospitals differed significantly from pre-COVID times. And so that's an interesting sort of way to create clinical shifts. And then you can also create shifts across sensitive attributes such as age, sex, and ethnicity, which is useful in understanding if your model is, again, performant across different patients or populations. The real challenge with monitoring a model across time, once it's in production, is that you don't have access to labels. So usually when you want to assess the model to see whether it is still performant, the standard way to do it is to simply evaluate the model if you have access to labels. But then in the absence of labels, or in the absence of, if you only have access to a few labeled data, what you're really looking at is only the shift in input and output distributions. And so one of the ways to capture that is using sensitivity tests. And so given a source and target data set, you can compute the distance between these two distributions using these tests. And so we've implemented a few different testing methods, such as MMD, univariate testing methods such as chi-squared test or KS test, which a lot of statisticians are familiar with. There are also other methods such as the learned kernel test, or a context-aware MMD test, etc. And in some cases, having access to the knowledge of which domain the data comes from can also be interesting and help with determining between the source and target distributions. So in those cases, we use like a domain classifier or a spot the diff method. And so the output of the shift detector module is basically an alarm which says whether a dataset shift has occurred or not. And it helps the team that is managing the model sort of make a call whether the model can be trusted or not. I'm going to go back to the slides here. Okay. So I want to just show you a quick example of the monitoring API. I hope you can see the new screen with the tutorial. So in this use case, we are using the popular NIH chest X-ray dataset. It is basically a publicly available dataset with chest X-rays. And we want to showcase how you can use the clinical shift applicator to apply some clinically relevant shifts, such as across the patient gender, and actually assess the different testing methods to see whether they can capture the applied shift. So in this case, we do some simple pre-processing because it's imaging data. And we apply, we use a dense net model to reduce the dimensionality of the input data into features. Here again, depending on the input modality, you can use different dimensionality reducing techniques. So in the case of tabular data, you can also use methods such as PCA and other methods such as autoencoders to reduce the dimensionality. And in this case, we're using a convolutional neural network such as the DenseNet. And we choose the detector, which is a regular sensitivity test, which is the MMD method. And across different sample sizes, where you have 50 samples, 100 samples, and 200 samples, we run a shift detection experiment. So in order to compare which method is able to detect shift more reliably. So for example, here we see that the BBSC plus the TXRV autoencoder dimensionality reduction method can detect shift even from a very small number of samples, whereas for the other two approaches, you need at least a few hundred samples to be able to detect shift. Now, the thing is that here you're expecting the model or the method to detect that a shift has occurred. And you want to do it with as few samples as possible, because in a lot of the actual production use cases, getting access to like 200 samples is very costly. So you really want to be able to say that a shift has occurred even with few number of samples. And so this toolkit really allows you to assess different methods to see which one can work well with the budget of allowed number of samples. We also have other examples where we can compare different models that were trained on different data sets. So for example, a model that was trained on NIH, another that was trained on the Chexpert model, and a third model which was trained on pad chest. So we're now comparing, again, using the same testing method, the same sample sizes to see which model is detecting an example shift over here. And the other types of shifts, including like looking at different patient subpopulations. So for example, here we're looking at shift between say the male population and specifically across like two different age groups. So this usually helps us understand also where a particular shift might be coming from. But the problem is you'll have to scan through all the different like patient subpopulation groups, which can be very expensive. All right. So I'll briefly be talking about the idea of a model card. So we built all these different APIs, which can create the sort of end-to-end ML ops system for deploying clinical ML models. But really, it's kind of hard to put them all together, given that they're all like different APIs, different fragmented things that are going on. And so the idea of a model card made a lot of sense, where first of all, it was a concept that was proposed in this famous paper called Model Cards. Sorry, do we have a question? Oh no, that was just an announcement. So this model card is a sort of standardized document which provides key information about an ML model. The goal, again, is to increase transparency and sort of make it the single source of truth about the model, how it's going to be used, different ethical considerations, performance, and other characteristics of the model. And so typically, for example, you can have a section describing the model architecture, another section describing performance, details of the models, its limitations, the quality and the actual data that it was trained on, as well as the shift or the drift of the data observed over time. So you're not just looking at a static picture here, you're looking at the model trend over time. So this really brings us to the idea of a transparency report, which is sort of perpendicular or in line with the model card, which I will just show in an example here. So what we thought about was that the idea of a model card is really, really interesting for healthcare ML models, where we can really start making or improving the transparency of the models that are being considered or even going towards deployment. And so this is an example of one such model card, the recently talked about model with which was a DenseNet model that was trained on the NIH chest X-ray model, chest X-ray dataset. So this is how it could look like, where you have different sections sort of talking about the model, starting with like basic details such as which dataset it was trained on, reference to any papers, citations, who are the intended users, what are the use cases and the limitations, other ethical considerations and sort of fairness considerations, and sort of giving the end user a quick overview of the different aspects related to the model. And you can have Cyclops to help perform quantitative analysis, so quantitative performance analysis. So earlier I showed you examples where we use the evaluate API to evaluate the model across patient subpopulations. So here is an example where this particular model classifies input images into different pathologies. So here we have pathologies such as like fibrosis, edema, hernia, nodules, etc. And so we can look at performance, which is measured by AUROC across the different pathologies, and slice them across the patient gender categories. So in order to obtain this particular analysis, we made use of the evaluate API, where again, like we divided the data set into multiple patient subpopulations, here specifically like male population and female population, and we can look at the performance. And really here you can see, like, for example, for one or two of the pathologies, there seems to be a somewhat significant difference between the different patient subgroups. So another example is age. So you can look at population performance across different age groups. And here again, like usually there are departments in a hospital responsible for patient care and quality of care. And so for doing these quality checks and assessment, this is really an important sort of metric, or this picture is very important, where they're making sure that a model is performing equally well across different patient groups. Similarly, you can have charts and plots for explainability analysis. So one such example is trying to explain where a potential shift in data might be coming from. So that's known as the drift sensitivity analysis. You can have fairness analysis, where you're looking at error rates across different patient subgroups. So here we've defined a certain base group, and we're looking at the error rate parities across different groups. So those groups which are closer to 1 are close to the actual base group, whereas those groups which are further away from 1 either are getting like better outcomes or better predictions or worse predictions, depending on which side they are. So the first question from Anna was about the performance of the queries themselves being slow compared to using SQL directly. Yes, so we make use of a library called SQL Alchemy, which which is basically a library that connects to different database implementations and runs queries. And yes, typically this library, it creates an object relational mapper, which then figures out what the different tables and queries are based on the different like relational logic that is being queried. And this does tend to be slower than actual SQL. But we did benchmark this for a few different examples, and typically for very large tables with very expensive joins, this does tend to be slower than raw SQL. But really, that's the thing with ORMs, is that they shine when you really want to have complex logic, as opposed to just using them for simple like relationships where you're just working with one or two tables. So for our use cases with these medical tables or with EHR data, there usually tends to be a lot of complex logic involved, where you're trying to combine multiple tables, have multiple conditions, filtering, etc. And so the trade-off between speed and the abstraction that you get is, we feel, is somewhat worthwhile. But as you mentioned, if you're just going to use one table and a very simple sort of query, then I think raw SQL would definitely be faster. All right, we have another question. How do you create a query other than Mimic? Is there a base class to extend? Is there an example of how you create your own query available? Yes, this is a good question. So we do have a base dataset querier, and all the other, like the Mimic querier, they inherit the dataset querier class. So if you want to query your own dataset, you can simply use the base class and extend it. And the querier actually does not talk to or does not deal with CSV files. It simply queries, or it simply talks to Postgres databases, and you can basically query, run your query, save the resulting data frame as like a pandas data frame. Of course, that data frame itself, you can save them as CSV files, and we have examples on the Cyclops webpage. So, for example, I can show you. This is probably what I missed because of the fact that I couldn't share my other tab. So there is a tutorial for the query API that I will share in a moment, where it will showcase how you can. So that's the link that I posted on the chat, where you can basically extend. You can simply create your own querier class and expand the dataset querier class. And the dataset querier, or the base dataset querier, is available in this file. There's not an actual tutorial explaining how you expand it. It's just simply like how you do with any Python class extension. So you simply import the base class and write your own class to extend it. The final question from Shahid is, can this scale and be containerized? That's a great question. So we are currently releasing sort of or very early versions of the framework as a Python package. So you can do pip install PyCyclops to install it as a Python package or a dependency into your project. We don't yet have so the whole project itself is not just meant to be a Python library, but rather a framework for developing end-to-end use cases, along with having a few examples where you can sort of implement deployment pipelines. So we're planning, our roadmap is to even have some integration with workflow orchestration, where you can easily define multiple tasks using the APIs and create an end-to-end workflow. And that's where we feel we will containerize that implementation and provide examples using sort of Docker images and Docker containers. But in the basic examples that I've showed, these are all using the Python package. And so if you just want to play around with it, the easiest way is to simply install the package or download the source code and start playing around with it in development mode. The final question from Shahid is, how can someone contribute to this repo? That's a great question. We are actually really looking for community contributors. So if anyone is interested to contribute, please check out the code base on GitHub, and do look out for potential issues or things you can contribute to. You can definitely create your own issues, or under the discussions tab, you can post your own ideas. And we do welcome contributions from the open source community, and that's really welcome. All right, I will continue with talking about our use cases. So now that we've been developing the framework itself, the whole point of it is to apply it to real world use cases. And so I'll be talking about the first use case that we're actually using this project for, which is delirium. So delirium is a state of acute confusion that affects 1 in 3 hospitalized adults. It is one of the leading causes of preventable harm in hospitals. It really increases morbidity, mortality, and cost to the overall healthcare system. And so, for example, when a patient is brought into the ICU, and this is especially more the case with elderly patients, is that they receive a lot of drugs, and they sometimes have very intense interventions, and this can really cause them to feel a lot of confusion and paranoia. They're not sure what's happening around them, and until they have like loved ones come and talk to them, they can sometimes feel very isolated and confused. And the issue with really is that like up to 40% of delirium cases can be prevented through a bundle of interventions. But the thing is that it's a big burden on the healthcare system to provide these interventions. So the thing is that we in today's hospitals, we can't even reliably measure delirium, because it's a mental state, and we only know after the patient has gone through the healthcare system that they were probably experiencing this condition. And so any good indicator of a condition such as delirium needs to have 4 important factors for it to be useful. So first of all, there needs to be the importance to measure and report it. And I think it's amply clear that in the case of delirium, it's very important to measure it, so that if hospitals have an idea of how much or how many cases of delirium is occurring in their wards, they can plan their staff and they can allocate resources accordingly. The next thing is that it's actually feasible to measure delirium using machine learning methods. So looking at patient chart data, their previous data from like previous encounters, the kind of medications that they're under, you can reliably predict if they have a risk of entering the delirium state. And so the feasibility, there are several papers that show that on retrospective data that you can reliably measure delirium. And so what is remaining to really turn this into a solid indicator is broad spread, like scientific acceptability. So you really need to have reliability and be able to validate that measuring delirium in whatever, using whatever ML method is sound and it's good, and be able to use it. So when you actually make decisions and when you inform the clinical team about the rate of delirium, what are the steps that they're taking to bring down the rate? So are they better allocating resources? Are they planning the nursing staff schedule in the right way? All of those things can really make the usability of such an indicator valuable. And so the 6 proven strategies to prevent delirium or address delirium is providing sound nutrition, providing some stimulation to the mind, moving, so just making the patients sort of move and not be sort of stuck and isolated and lethargic, making sure that they sleep well, and ensuring that their seeing and hearing abilities are proper, providing them with hydration. And the thing is that all of these things are very all of these things are place a burden on the healthcare system. And knowing how to prevent them is one thing, but then if you cannot measure delirium accurately, it's very hard for the hospital to even know how to allocate resources. So we are currently in the middle stages of our project, where we have managed to validate a quality indicator. So we know that our model, which measures the incidence of delirium, is correct, in the sense that we have looked at a broad data set of retrospective patients, and we used various features to predict the rate of delirium. And we are now in the process of creating a scorecard where which reports delirium incidence and prevention process measures to decision makers, which are the hospitals and the teams in hospitals which are responsible for patient care. But the thing is that despite having a scorecard to report delirium, as well as like a validated method which provides indicators for delirium, in order to adopt this, you really need the stakeholders to have trust in the models and the overall system. And so you need some sort of transparency or a tool that can provide transparency to the models that are being used. And so the example that I showed with the transparency report that was generated through Cyclops, we believe is a way forward to report the reliability of the models. And so with each sort of new refresh of the data, the decision makers know, okay, can we trust the model now? Or do we need to update it, or do we need to change something in the overall ML pipeline to make sure that the model is reliable? And so the next step is that once we've managed to really have the toolkit implemented and have the overall pipeline working, we will have actual prevention methods tailored to address barriers in Canadian hospitals, and have dedicated interdisciplinary teams at each hospital, led by specialists to come together and address the problem to drive delirium rates down. So our project is currently in AIM 2. So we've already sort of developed the quality indicator as well as a model for measuring the rate of delirium. We're currently developing a scorecard and ensuring that the model performance can be monitored over time and does not degrade. And so we at least have a monitoring shift system. And after we complete this phase, we will tailor the delirium prevention approaches for each hospital using different implementation science methods, and finally sort of evaluate it across multiple hospitals as well. At the moment, we are piloting this report to one hospital stakeholder. So we, along with our partners at Unity Health, who are developing this model, we are providing rates of delirium measured across different quarters. So, for example, this is kind of a sample of what the hospital stakeholder sees, where for one quarter, we measure the rate of delirium, and then we provide a trend of this over time so that they can see whether the rates of delirium are actually coming down, and they can take sort of high-level decisions to change, care practices such that they can drive these rates down. We also provide patient demographic information and sort of reports to help improve the transparency of the actual model. And this is currently what we are hoping to deploy with Cyclops. Another example collaboration or an actual deployment project is a chest X-ray classification model. And this is in collaboration with Trillium Health Partners. So it's a community-based hospital in Mississauga. And we started out with a simple sort of research question where the radiology department at Trillium Health Partners, they came to us and said, we have chest X-ray images, and we want to build an automatic system that can classify pneumonia using these chest X-ray images. We've looked at a lot of open source models that can do this, but we're not yet sure how to deploy these models in our hospital. So first of all, we wish to evaluate how these open source models or freely available models generalize to our data. And the problem is they don't have even labels for their data, for their hospital data. So the best we could do was to analyze these models for potential data set shift, and also help sort of conduct research on how data set shift detection methods work for different sources of shift, so that in the future, when they do consider deploying this model, they have ways to sort of assess different shifts that occur and how they degrade model performance. And so the pipeline looks like this. We talked about the monitoring API. So we made use of the monitoring API to take samples from a source distribution and a target distribution, reduce the dimensionality, and then have two sample statistical tests to say whether the target distribution differs significantly from the source distribution. This particular data set had roughly 3 periods. So there was the pre-COVID period before sort of 2019 as a sort of control period. We took data from 2018 to 2019 June. And then we had the COVID period, which is starting from March 2020. So this is specifically looking at data set shift that occurred because of COVID. And so we assess different sort of sensitivity tests pairing with dimensionality reduction methods. And for each sort of group, we took around 5,000 samples and sort of kept increasing the number of samples to measure how well the shift detection methods capture the detected shift. And we also compared different sort of methods, such as having a trained autoencoder versus other dimensionality reduction methods, as well as like two sample tests and other distance measuring methods such as MMD. And finally, we found that a trained autoencoder with MMD had sort of the best performance for as a detector. So one example is looking at the pre-COVID to COVID domain, as well as having the reference or the control group, which is simply the control period to the pre-COVID period. And so you can see that like with almost like an order of magnitude less samples, you see a detected shift for the pre-COVID to COVID period, indicating that okay, because of COVID, there has been some shift in the input data, and this could potentially be problematic. And so you need to inform like radiologists who might be using the model to at least tell them that like, hey, look, like because of COVID, there is a shift in data. So whatever model you're using, it's time, it needs to be updated if it hasn't already been, or if you cannot update it, then you need to trust it less. Similarly, we started segregating these samples into finer examples, and one such example is we specifically looked at if the samples came from the ICU or not. And it turned out that because a lot of COVID patients were admitted to the ICU, those samples that came from the ICU had a higher degree of shift when you looked at control groups as compared to those samples which didn't come from the ICU. So I finally want to talk about challenges with implementing monitoring in for healthcare use cases. So today, with some of the methods that we have incorporated into the Cyclops framework, we can detect covariate shift reliably. So the plots that you were seeing, where you have p-values indicating when there's a statistically significant shift. The problem is that when we were implementing these approaches with our stakeholders at THP, the clinicians not just wanted to detect when shift occurs, they actually wanted to also know the source of the shift, or be able to explain the source of shift. So for example, in this case, we are already taking samples from like different distributions, which we know are likely to be different, like for example, pre-COVID and COVID, or different genders and so on. But then in the real world, when you deploy it, if a shift occurs, and if your algorithm says, hey, look, the current data set is shifting, we don't yet have a method which says what is the reason for that shift. Is it because there is a different set of population or a different demographic that is coming in, or is it because a clinical practice has changed? Like, what is the reason for this shift? That's really what clinicians want to know. And the second problem is we cannot yet correlate the detected shift reliably with deterioration in model performance. So even though covariate shift happens and we can say, yes, okay, there is a shift, we can, if you look at the model performance, it might be completely unaffected, in which case, like, the clinicians don't really care, because as long as the model is performant, they're okay if there is some shift in input data. And again, it depends on the case, because sometimes they do want to be informed that the input data is shifting, and sometimes they just don't care because it's not that important. So really what they are important in is knowing when something dramatically changes in the input and it affects model performance. And they're also sometimes interested in knowing when inputs change dramatically, but it might not change the model performance. And the problem is that, like, for these two things, we don't yet have the answer. And it's currently an open question, and we are working with our research faculty affiliates at Vector to address these two problems before we're ready to productionize the monitoring toolkit. Finally, I want to give a shout out to our stakeholders and collaborators, specifically Trillium Health, the Gemini Initiative, which is one of the largest retrospective data sets in the world, It captures around 70% of Ontario's general internal medicine and ICU data. And it's the data set that we use to sort of conduct all our experiments and sort of develop our use cases on. Also, shout out to Unity Health, our collaborators who have given us access to data, as well as the ones engaging with us on the delirium use case. And finally, my teammates at Vector, who have been part of the development of the framework. And that's the end of the talk. Thanks so much for listening, and sorry for the technical glitches earlier. Please do check out our GitHub repo if you're interested in our work, and our landing page and documentation page also, which is present on the GitHub repo. All right. Thank you so much for attending the talk, and have a wonderful day and enjoy the rest of the MLS.